Welcome to Fundamentals of DC Circuits. My name is Professor Evans, and this is the first video in the lecture series for this course, which is EET10105C at Valencia College. Before you begin watching each video, please make sure that you have printed out the lecture notes that are available on Canvas and fill them out as we complete the video together. This first video will cover energy and power. The objectives for this video are to be able to define the terms energy and power, to be able to calculate the power in a circuit, to be able to select resistors based on a power consideration, and to discuss the characteristics of DC power sources. To begin, we'll start with the basic definition for energy. Energy, which is represented with a capital W, is the ability to do work or to apply force to move an object. When it comes to electronics, electrical energy is a form of energy that results from the flow of electric charge. Electrical energy may be either potential or kinetic, but it's usually encountered as potential energy, which we define as energy that is stored. Power, which is represented with a P, is the rate at which energy is used. So for this video, we'll be discussing the concept of power, and power is based on the concept of energy. Power is a rate, so it's how much energy is used in a particular unit, and energy is the ability to do work or apply force to move an object. So again, power is a rate, so it is the amount of energy used in a particular unit of time. The formula that we'll use to calculate power, well, one of many, is work divided by time. The W here also stands for work. So sometimes energy and work will be interchangeable terms. Again, the ratio to calculate power is work or energy, which is the W, divided by time. Keep in mind that power is measured in watts. That's the unit that you'll use for power. Energy is measured in joules. That's the unit you'll use for energy. And then time is measured in seconds, or it could be milliseconds, microseconds, some derivative of seconds. Remember that we previously discussed in another class that voltage is defined as energy or work per unit charge. So we have two concepts, voltage and power. They're very different concepts, but they both rely on looking at the amount of energy that is consumed. Voltage is energy consumed per unit charge, and power is the energy per unit time. So notice that the denominator for both of these equations is different. And that's how we differentiate between the idea of power and the idea of voltage. Electrons flow through a resistance, a voltage drop is created because the electrons lose some of their energy as they exit each resistor. If you look at this diagram here on the screen, we have a voltage source. The voltage source has a positive and a negative terminal. Remember that whenever we think about the flow of current in a circuit, the flow of current begins from the voltage source and it exits from the positive terminal. So electrons are going to flow out of the voltage source this way around the circuit. As those electrons travel through the circuit, if they encounter a resistance, for example right here or right here, well, a voltage drop is created. We can see that that is noted on the diagram with a plus and a minus. I'm going to highlight those. The plus and minus here indicate the polarity of the voltage drop. Basically, that means if I were to measure the voltage at this point before the resistance and then measure the same voltage after the resistance, we would see that there would be less voltage. There's a drop in voltage as the current flows through the resistance. That resistor right here and right here is going to impede the flow of current, causing some of the energy to be lost in the circuit. That energy is lost in the form of heat as the electrons flow through each resistance. So as we go throughout this course, we're going to begin to label every voltage drop that occurs within a circuit and eventually learn how to calculate each voltage drop in a circuit. So be very mindful of the polarity it's very important that when you label a voltage drop across a resistance, the terminal that current enters is the positive side, where current exits is the negative side. You're always going to have to remember polarity. Polarity will be a huge factor in this course. So as you're labeling your voltage drops, keep in mind the positive end of your voltage drop is where current enters. The negative end of your voltage drop is where current exits when it comes to labeling these voltage drops across resistors in a circuit similar to this one. You can see also at the bottom that this diagram explains what happens with the energy level as electrons flow through a circuit. As they leave the voltage source, this is when they have the most energy. As they travel through each resistance, the electrons lose some energy. By the time they return back to the voltage source, that's the least amount of energy that those electrons have. Energy can also be expressed as W equals P times T, or work equals power times time. Basically, we're taking that first equation and just rearranging it so that the W is on the left. In this form, the units of energy are in watt seconds. So if we were to rearrange that first equation, we basically have on the right-hand side power times time, which means that the unit for energy becomes a watt second, or a watt hour, or a kilowatt hour, depending on how large this value is. A common unit of energy is the kilowatt hour, which is how you are billed for your power use by the electric company. If you've ever looked at a bill from an electric company, they determine the number of kilowatt hours you've used in a month and then bill you based on a certain rate that they charge for each kilowatt hour. So as an example, if you have a 100-watt light bulb that is burning for 10 hours, it would use 1 kilowatt hour of energy. And we come up with that number by using this formula here, where we plug in the power, which is 100 watts. We plug in the amount of time, which is 10 hours. 100 times 10 will give you 1,000, and our unit here would be watt hours, because we're multiplying watts by hours. But then using scientific notation, or rather engineering notation, we will convert this to 1 kilowatt hour. And then your electric company will bill you for each kilowatt hour that you use in a month. Next, we're going to talk about the power in a circuit. The amount of power dissipated in an entire circuit is dependent on the amount of resistance in the circuit and the amount of current. We have some formulas here that we can use to determine the amount of power dissipated in a circuit. Power can be determined by taking your current squared times your resistance. It can also be calculated by taking voltage times current, or you can take the voltage squared divided by resistance. Any one of these formulas can be used to calculate power in a circuit. And honestly, you'll end up choosing the formula that fits best depending on the information you have in a particular problem. The relationships between power, current, voltage, and resistance are known as Watt's law. So we've already discussed Ohm's law, and now we have Watt's law, which gives you those relationships for power. Keep in mind that if you're using this to find the power in a circuit, you need to know the total current in the circuit, the total resistance in the circuit, and or the total voltage applied to the circuit. Also remember your units as you're calculating answers to problems. Every answer needs a unit. So if you're calculating power, power should be in watts, current should be in amps, resistance should be in ohms, and voltage should be in volts. Here's the first problem in the lecture notes. What we're going to do is basically practice applying Ohm's law. We have 3 different circuits, and we're going to calculate the power for each one. Here's a reminder of the formulas that were displayed on the last screen as a reference. So first we'll start with circuit A. Notice that circuit A has a 10-volt source. The polarity is labeled, so we know that current exits this way, travels around the circuit, and then returns through ground. We know the value of the voltage source is 10 volts, and we know the value of the current in the circuit is 2 amps. We don't know what R is. Using Watt's law, we can calculate the power by saying the power has to be the current times the voltage. That's one of our 3 options we have for calculating power. Remember to plug in your units. So I have 10 volts multiplied by 2 amps, which gives me a total of 20 watts of power for this circuit. In circuit B, we don't know what the voltage source is. We have a polarity, we know which way the current flows, but we don't know how much voltage has been applied. However, we do know the current going through the circuit, and we know the value of R. So now we can use I squared times R as our method for calculating the power in this circuit. So we would simply do 2 amps squared multiplied by 47 ohms. The power in this circuit is 188 watts. And then finally, for the third circuit, we have a voltage source, we have a polarity, so we know current has to flow this way. And we have a resistor of 10 ohms. What we don't know is how much current is flowing through the circuit. Now, if you wanted to, you could use Ohm's law to calculate the current flowing in the circuit and then use one of these 2 formulas here. Or you can just use the third formula, which says that power is V squared divided by R. So take your voltage, which is 5 volts, square it, and then divide by 10 ohms, you'll get 2.5 watts. This is a quick and easy application of Watt's law using each of the 3 formulas provided, and they're based on what you're given in the circuit. However, at any point in time, you're always welcome to use Ohm's law to solve for a missing resistance, a missing current, or a missing voltage, and then use that information to plug into any one of these 3 formulas for Watt's law. But let's just say, if you're looking at circuit C, for example, if you didn't need to know the current, using this formula here just saves you the step of having to calculate something you really didn't need anyway. So you'll have to use your best judgment on when you need to use Ohm's law and when you'll need to use Watt's law, depending on what you've been given and what you've been asked to find. So, as we discussed earlier, when there is current through resistance, the collision of electrons will produce heat as a result of the conversion of electrical energy. So anytime you have current flowing through a resistor, there will be some energy that is lost because heat is created. It's a transference of energy. And in the circuits that we'll build in lab, this will happen. However, your circuits will never become hot enough that it should burn you or anything like that, but there is going to be a small loss of energy because heat is produced when current flows through a resistor. Because of that, every resistor has a power rating. It's the maximum amount of power that a resistor can dissipate without being damaged by excessive heat. So resistors can burn up. If there's too much power applied, if the current is too high, a resistor can literally, the legs of the resistor will burn or melt if there's too much heat. And you'll literally see the legs of the resistor break off and the resistor will become too hot to touch. Again, this should never happen in your laboratory scenario. All the circuits that we're going to give you to build have been designed so that this should never happen. If it does, we know that there's a mistake in the circuit somewhere. But as you're building electric circuits, you have to be aware of how much power your components can handle, because if you overpower them, then you have your circuit becomes hot and you have components that will fail. So the power rating for a resistor lets you know how much power that resistor can tolerate without being damaged by excessive heat. The power rating is not related to your resistance value. So you can have a 100 ohm resistor, a 1 kilo ohm resistor, a 100 kilo ohm resistor. They're all going to have different power ratings based on the manufacturer. The power rating is determined by the physical composition of the resistor, its size, and its shape. The standard power ratings for resistors are 1/8 of a watt, 1/4 of a watt, 1/2 of a watt, and 1 watt. When a resistor is used in a circuit, its power rating must be greater than the maximum power that it will have to handle. So when you're designing a circuit, every resistor will have a power rating. You always want to make sure that you have a buffer for safety so that your resistors will never burn up due to excessive heat. For example, if you have a resistor that's going to dissipate a maximum value of 0.75 watts in a circuit, you'll want to select a resistor with the next highest power rating, which is 1 watt, so that you have a safety margin there, and that your resistors will not burn up due to excessive power. Now 1 watt is the least next higher standard. You could pick a 2 watt, a 5 watt, a 10 watt resistor if you wanted to, but you need a minimum of a 1 watt resistor. You need that power rating to be at least 1 watt for safety. As in any circuit, you should always choose a rating that is larger than the actual power so that you have a buffer for safety. So if you look on your lecture notes, the next problem is about resistor power ratings. It says choose an adequate power rating for each of the resistors below. Let's start with the circuit on the left, circuit A. First, analyze what you've been given. You have a 10-volt source with the polarity labeled here. That means current is going to leave the source, travel around this way, and go this way. We don't know how much current is in the circuit by the diagram, but we do know that the resistor value is 120 ohms. Using our power formulas, we can determine that the total power, or the maximum amount of power that this resistor will dissipate, is going to be 10 volts squared divided by 120 ohms, which comes out to be 0.833 watts. So we need to make sure that we select a standard power rating that is higher than the 0.833. Remember, your standard ratings are 1/8 of a watt, 1/4 of a watt, 1/2 of a watt, or 1 watt. So in this case, you're going to select a power rating of 1 watt to make sure that that resistor can handle all the power that's being generated in this circuit. Now take a look at circuit B. In this picture, we have a voltage source. We don't know how much voltage is applied, but we have a polarity and we know that current flows this way. We know the value of that current is 10 milliamps, and you have a resistor of 1,000 ohms. For this circuit, we'll use P equals I squared R to figure out the power that is dissipated. Plug in your value of current. Remember, this is milliamps. Make sure that you type that in your calculator appropriately. 10 times 10 to the negative 3. So 10 milliamps squared times 1,000 ohms gives you 0.1 watt. So you can select a power rating of 1/8 of a watt because that's 0.125 watts, or anything higher. This is the lowest one you can select. You can always go higher than that if you wanted to. This is how we consider the amount of power that might be dissipated in a resistor and select the appropriate resistor for that application so that you don't have an issue of your resistor burning up due to excessive heat. In this next example, we're going to determine whether the resistor in each circuit below has possibly been damaged by overheating. So we have 3 circuits provided, and with each circuit we have a resistor value as well as a power rating. So what we're going to do is look at each circuit, determine the amount of power that'll be dissipated in this resistor given the circuit, and then we'll determine whether the rating is sufficient or whether there may be a potential for damage due to overheating. So with the first circuit, circuit A, we have a 9-volt source with a polarity labeled here. We know current will flow this way. And as current flows through that resistor, a certain amount of power will be dissipated. Let's calculate that amount of power and determine if this rating is satisfactory. So I can calculate the power by doing V squared divided by R. Notice that I don't have the amount of current in the circuit. Yes, I could go find it using Ohm's law. Do I particularly need to in this scenario? Not necessarily, because I can use V squared over R to determine the power, and that's really the only thing we need right now. So if you look at the voltage, it's 9 volts. So we have 9 volts squared divided by 100 ohms. That'll give you 0.810 watts or 810 milliwatts. This power rating is therefore insufficient because 1/4 of a watt is far too low, and this resistor is definitely in danger of being damaged by overheating. Next, take a look at circuit B. In this example, we have a 24-volt source. Polarity is here. We have a 1.5 kilo ohm resistor with a power rating of 1/2 of a watt. So first determine the power dissipated in this resistor. For this, we can also use V squared over R. So you have 24 volts squared divided by 1.5 kilo ohms, which gives you 0.384 watts or 384 milliwatts. The power rating here is a half of a watt, which would be 0.5 watts. Since that is higher than 0.3 watts, the power rating is adequate. And this circuit is not in danger of being damaged by overheating. In the third circuit, we have a 5-volt source, a 10 ohm resistor, and a 1 watt rating. The power dissipated for this resistor would end up being 2.5 watts because you'll do 5 volts squared, which is 25, divided by 10. You get 2.5 watts, and this only has a 1 watt rating. So this power rating is also insufficient, which means the circuit is in danger of having damage due to overheating. There's simply too much power for this resistor to handle. So you can still use a 10 ohm resistor, you just need to select one that has a higher power rating, something that is higher than the 2.5 watts that is calculated here. Next, we're going to transition and talk about power supplies. So in each of the circuits that we've discussed so far, there's been a source, a DC voltage source. It's been labeled with a positive and a negative terminal. And when we build a circuit like this in the lab, we'll use a power supply to deliver the 9 volts that is needed in a circuit like this one. So a power supply is going to be found on each of your lab stations when we get to the lab. You'll learn how to use it during the course of the semester. The power supply plugs into the wall. The wall delivers an AC voltage, which is an alternating voltage. It looks like this. It's a sine wave that changes with time. The power supply will convert that alternating voltage to a DC voltage, a direct current voltage, something that is constant, like 3.3 volts or 5 volts or 12 volts or whatever voltage you need. Your power supply will plug into your wall, take that AC voltage, convert it to a DC voltage, and then allow you to supply that DC voltage to your circuit. So today we're going to talk a little bit about what those power supplies can do. In our lab, we will use the Hammock triple power supply. This is what it looks like. When you get to lab, you'll be able to locate this on your bench. I'm going to go over a few of the settings for this power supply. The power button is actually right here to turn it on, right there in the middle. Again, this is a triple power supply. It is used to deliver DC voltages, direct current voltages, meaning a voltage that does not change. And the focus of this entire course is to study circuits where the voltage source doesn't change. After this course, you'll take fundamentals of AC circuits, where you will study circuits where the voltage changes with time, and again in the form of a sine wave. So in the next course, you'll study circuits where your voltage is constantly changing. And circuits will behave differently when that happens. But for now, this course will only focus on DC voltages. So in the lab, you'll set this power supply to a certain voltage level, and then it'll stay at that level for the duration of the lab. And you can manipulate that with changing the knobs, like here. It has 3 ports. The ones on the left and the right can give you anywhere between 0 and 20 volts, and it'll give you 0.5 amps of current. So you will manipulate this knob, and you can get anywhere between 0 and 20 volts. The one in the middle gives you only 1 voltage. It gives you 5 volts and nothing else. So as we're doing our labs, you'll want to make sure that if you need something other than 5 volts, you'll use the port on the left or the port on the right, and you'll use the knob to set the voltage that you want. Again, this one here is only if you need exactly 5 volts, and it'll give you exactly 1 amp of current with those 5 volts. The efficiency of a power supply is the ratio of output power to input power. Efficiency can be described with the equation on the screen. Again, it's a ratio. Power out divided by power in. Output power is the power delivered to your circuit. So once you connect your alligator clips to your power supply, you build your circuit, the output power is the power coming out of the power supply and being delivered to your circuit. The input power is what the power supply receives from the power outlet in the wall. Again, your power supply will be plugged into an outlet from the wall, and then it will deliver power to you. So power coming in is what the power supply receives from the wall, and the power out is what the power supply delivers to your circuit. You'll always have some power loss due to the nature of your power supply, and your output power will be determined by your input power minus that loss. So if we look at our Hammond triple power supply, we're now going to determine the total power supplied if the maximum voltage is used for all 3 outputs. Remember, the outputs on the left and the right have a maximum of 20 volts with a current of 0.5 amps, and the output in the middle has a maximum of 5 volts with a current of 1 amp. So if we were to determine the maximum power supplied by the triple power supply, here's how we would do that. The power for the outlet on the left is 20 volts times 0.5 amps, current times voltage, plus the power for the output in the middle, 5 volts times 1 amp, plus the power for the output on the right, which is 20 volts times 0.5 amps again. So you get a total of 25 watts. So that is the total amount of power that this particular power supply can provide. Again, that's if you're connected to all 3 outputs and you have them set to the maximum level of voltage. So let's say that we have a certain electronic power supply. It requires 25 watts of input power, and it can produce an output power of 20 watts. What is the efficiency and what is the power loss? So let's start with the efficiency. Efficiency is power out divided by power in. Oftentimes we multiply that by 100% to get a percentage. So the output power was given as 20 watts. The input power was given as 25 watts. Simply take that as a ratio, multiply by 100%. It has an efficiency of 80%. 80% of what goes in will come out. There is going to be 20% of loss due to the nature of the power supply itself. And lastly, the power loss is simply what goes in minus what comes out. 25 watts went in, 20 watts came out, there was a loss of 5 watts of power. And this is how we calculate the efficiency of a power supply. Depending on the system you're designing or the type of circuit you're building, you may need a certain level of efficiency from a power supply. So when you select the power supply you're going to use, you would have to look at the specifications or the user manual for that particular supply and ensure its efficiency is where you want it to be. Generally, we try to avoid using power supplies that have a really low efficiency because you're losing energy. The power lost is not power that is delivered to your circuit, it's simply lost. So we try to look for the efficiency level to be as high as we can whenever we're designing a circuit that has to use a power supply. And that is the end of this video.